Welcome back to our introductory course on machine learning. We are in Unit 4 talking about neural networks, and in this video we're going to be talking about training procedures. So how do we actually fit a neural network to our training data? What are the parameters involved with that? And what are some of the methods that we can use to improve our performance? So we've been throwing around terms like gradient descent, backpropagation. Now we actually get a look at the parameters that you will use to tune those processes and produce, hopefully, good results. So let's get started. Like we have mentioned, neural networks are fit in using gradient descent in a process known as backpropagation. Gradient descent has various advantages. It is simple. It is local, namely the change in weight uses only the values of the presynaptic and postsynaptic units and the error when suitably backpropagated. When online training is used, it does not need to store the training set and can adapt as the task to be learned changes. Because of these reasons, it can be, and often is, implemented in hardware. But by itself, gradient descent unfortunately converges slowly. So this is going to be our first issue. Gradient descent is difficult to get to converge in the first place. Secondly, it doesn't happen very quick. So we're going to talk about several methods to speed up our convergence and improve that process and make it happen quicker. Secondly, neural networks are generally over-parameterized. As a result, we're going to see that it is very easy to overfit the training data. Remember, overfitting means that our network is too closely fit to the training data and can't generalize to new instances when generalization is everything. So over-parameterization is an issue for neural networks and something that we need to avoid. The third issue is that the optimization problem is non-convex. What this means is that it possesses many local minima. So in order to ensure that we are actually producing the best results, we're going to have to run these networks several times, and we're going to look at what that means in a second here. But in general, it's just important to note that this optimization problem isn't going to produce a guaranteed global minima every single time. So we want to account for that when we're actually training our network. But in general, these are the three issues with gradient descent and backpropagation. They're slow to converge, they're generally over-parameterized, and the optimization problem is non-convex. So let's take a look at some of the methods that we can use to avoid these three issues, because ultimately that's what's important. The first, and that is to improve convergence, is our starting values. Usually starting values for weights are chosen to be random values near zero. Because of this, the model starts out nearly linear. If you remember our sigmoidal function, near zero, that function is actually linear. So as a result, this is going to become nonlinear as the weights increase. Individual neural network units localize to directions and introduce nonlinearities where needed. Use of exact zero weights is actually going to lead to zero derivatives in the start and perfect symmetry. As a result, this algorithm would never move. Starting instead with large weights often leads to poor solutions. So we need to find the happy medium where we have random values near zero, so we're going to have derivatives that exist and cause our algorithm to move in either direction, but not so large that we are going to get poor solutions. Larger weights will overvalue the relative inputs, and as a result, we can produce poor results that way. So we're going to talk about some different methods here that are going to help our parameters stay within the ranges that they need to, so we can generalize well to new data. And those methods are momentum and an adaptive learning rate. We're going to start by talking about momentum. At each parameter update, successive weight values may be so different that large oscillations may occur and slow convergence. When we're talking about momentum, we're going to introduce T, which is the time index, and that is going to be the epoch number in batch learning and the iteration number in online learning. The idea is to take a running average by incorporating the previous update in the current change as if there is momentum due to previous updates. The formula that we're going to use for that looks like this. So alpha here is going to be our momentum. and alpha is generally taken to be between 0.5 and 1. And this approach is especially useful when online learning is used, where as a result we get an effect of averaging and smoothing the trajectory during convergence. So the disadvantage is that the pass weight value should be stored or need to be stored in additional memory. So we talked about one of the advantages of neural networks being in general, or online learning with neural networks, is that we don't have to store all of the data and all of the weight values, but instead we can only use the most current ones. So using momentum is going to add an additional set of weight values. In general, this isn't going to be that computationally important, but if we're using a hardware application, this does have to be considered. But momentum is a great way that we can avoid fluctuations in our parameter updates and actually improve our convergence and speed our convergence. The next way that we do that is the adaptive learning rate side of this. And in gradient descent, the learning factor determines the magnitude of change to be made in the parameter. It is generally taken to be between 0 and 1, mostly less than or equal to 0.2. It can be made adaptive for faster convergence, where it is kept large when learning takes place and is decreased when learning slows down. Thus, we increase the learning rate by a constant amount if the error on the training set decreases and decrease it geometrically if it increases. So all we're doing is we're going to control our learning rate such that it is an appropriate value for the stage of training that we're in. At the start of training, we expect large gains and large improvements. As a result, we're going to have a larger learning factor so that we can make those big jumps. As we get to the end where learning slows down, we're going to decrease the learning rate so that we can kind of fine-tune our network. We're not going to want to make as big of jumps because at this stage, we don't expect big jumps in improvement. So adaptive learning is one way that we can really speed up convergence. We are going to make large jumps at the start, so get closer quicker, but at the end we're going to lower that learning rate back down so that we don't make inappropriate or inaccurate jumps towards the end. So all of these methods are used because neural networks easily overfit and overtrain. So neural networks with too many hidden units will overfit the data. In general, we can't control the number of inputs we have. The type and set of training data that we have is set. The number of inputs is set. Also, the outputs are constrained as well. If this is a regression problem, we only have one output. There's classification. We're going to have as many outputs as we have class. But what we can control is the number of hidden units. We mentioned before that we're typically only going to use one layer of hidden units. If we're doing deep learning, we can have multiple hidden layers. In the next video, we'll talk a little bit about when and why we would have multiple hidden layers. But for now, let's just assume that we have one layer, one hidden layer, and all we need to control is the number of neurons or nodes in that hidden layer. So we know from previous videos that an overcomplex model memorizes the noise in the training set and does not generalize to the validation set. Neural networks are going to do exactly the same thing. So they follow the bias variance trade-off, which we've talked about first. If we make large assumptions or we make our data very complex, we are going to overfit the data. If we don't make it complex, we have very few hidden units. We may not be able to match the underlying trend of the actual data, so we might not be complex enough. So we need to keep this in mind when we're designing the structure of our network. We need an appropriate number of hidden units for our data so that we can avoid overfitting. We also have methods of regularization, which are going to help our networks generalize to new data. And that is really what regularization is. It's avoiding overfitting and overtraining so that when we get new instances, we are able to accurately classify those instances. And the first method is early stopping. When training is continued for too long, as more training epochs are made, the error in the training set is going to decrease, but the error on the validation set will start to increase beyond a certain point. Remember that initially all the weights are close to zero and thus have little effect. As training continues, the most important weights start moving away from zero and are utilized. But if training is continued further on to get less and less error in the training set, almost all the weights are updated away from zero and effectively become parameters. Thus, as training continues, it is as if new parameters are added to the system, increasing the complexity and leading to poor generalization. So learning should be stopped early to alleviate this problem of overtraining. Overtraining is essentially adding complexity to our network, and as a result, we overfit the data. The next thing that we can do is called weight decay. So weight decay is simply adding a penalty to the error function. In weight decay, lambda is going to be our tuning parameter. So large values of lambda will tend to shrink the weights towards zero, or large weight decay will shrink the weights towards zero, or smaller values won't shrink the weights as much. So cross-validation is typically going to be used to estimate the weight decay parameter or the lambda parameter. It's hard to predict what this value will be beforehand, simply because data is very diverse and one value of weight decay is not going to fit for every set of data. But it's another good method of regularization. There are other methods out there, such as dropout layers, which randomly removes different nodes so that the other neurons have to pick up the slack. And this is another way to kind of smooth the weights and prevent some weights from getting too large and overfitting the training data. But we're not going to talk about that as much now. It may come up in our next video when we talk about deep learning and convolutional neural networks in a little bit more depth, because dropout is typically used with deep learning networks. All right, so this is going to bring us to the end of our video on training procedures. In a quick summary, we use gradient descent and backpropagation to fit our networks. However, those run into the issues of slow convergence. They're generally too complex and over-parameterized, and the optimization problem is non-convex. We solved that first non-convex problem by starting with random values near zero and doing this multiple times. So zero weight equals zero derivatives. We don't move at all, but large weights are going to lead us to the wrong local minima and result in poor solutions. So in general, starting with random values near zero is going to be beneficial, and doing that several times. We can use things like momentum, which is incorporating the previous updates into our parameter changes to kind of smooth the trajectory towards convergence, and that value is typically between 0.5 and 1. We can also use adaptive learning rate, which is updating our learning factor as training goes on. The learning factor can be between 0 and 1, is typically less than or equal to 0.2. To avoid overfitting and overtraining, we are going to try to match the complexity of our model with the complexity of our data, and we get to control the number of hidden units, not the inputs and outputs. We can also use several methods of regularization, such as early stopping and weight decay, and those as well are going to improve generalization. In our next video, we're going to talk about convolutional neural networks and deep learning, so that's going to be very exciting because there's a lot of cool stuff going on with those. Thank you for listening to this video, and I hope it allows you to produce models and networks that converge accurately and quickly and can be used for a variety of different tasks. Thank you very much.